Okay, welcome everyone. Welcome to those who just came in. So I'm going to be talking about Cedar. I think I first probably need to start with a quick glossary. Cedar is pretty big as a project, so there are several terms that you may hear which refer to very specific things, but sometimes can be a little bit confusing. So Cedar is everything we're talking about, all the packages, all the packages and the product, everything you're about to see is Cedar. There's also Cedar EDA, which is a particular distribution of Cedar, specific versions of all the packages, as well as some integration into the Julia Hub Cloud platform. So that's Cedar EDA. There's Cedar Waves, which is the plotting and analysis thing that you saw in the live demo, the little widget on the right-hand side. There's Cedar Sim, which is the actual simulator. And then there's DAE compiler, which I'll be talking about some as well, which is the core compiler technology that is powering Cedar. So for this talk, I want to focus mostly on Cedar Sim and DAE compiler. It's a little bit different from what I promised I would do in the abstract. Some talks got consolidated, and I also already gave a previous talk about some aspects of Cedar at LatchUp, so I wanted to not be too redundant. So if you're more interested in using Cedar as an end user, I think the LatchUp talk will probably be more interesting to you. The link is on the slides. But what I want to talk about today is how does Cedar work under the hood, how is it implemented, and in particular, how are we leveraging Julia in the implementation of Cedar. So I think Cedar is different things to different people. It is, of course, a high-performance SPICE-compatible analog circuit simulator. So for people who are using things like Spectre or HSPICE or AFS or open source simulators like ngSpice or Zeiss, in the fullness of time, you should be able to just use Cedar as a replacement for a simulator like that. But Cedar is more than that. You can think of Cedar as an implementation of multiple programming languages common in this domain, Verilog-A and SPICE in particular. You can think of Cedar as a technology demo for using the Julia compiler technology to apply it to other programming language. You can think of Cedar as the reason we have effects, exception types, semi-concrete evaluation, optimized generics, and a bunch of other goodies in the Julia compiler. All of those are not Cedar specific, of course, and some of those were ideas that existed before Cedar. But Cedar was, Cedar was the reason that we ended up actually implementing them in the Julia compiler. It's implemented as a set of composable packages, as is common in the Julia ecosystem. So if you want to build something that's not quite a circuit simulator, but needs to interface with data structures from this domain, needs to interface, needs to do something with circuits, you may be able to just reuse part of the Cedar stack for what you want. And it's very deliberately kept as separate and independently usable Julia packages. Lastly, there's a little bit of an exploration for what high-level synthesis might look like in Julia. I'll touch about that a little bit. Some of you may remember the FPGA demo I did at JuliaCon in Baltimore 5 years ago. So this is a little bit more evaluation on that thinking, and we'll be doing more thinking on that over the next year or so. And lastly, it's on GitHub. It's mostly MIT licensed. Some parts are CERN OHL SV2. If you're interested in why that particular license choice, also see the other talk where I dive more into the motivation. I will caution that I have not fully completed opening up the repositories yet, so the version that's on GitHub is probably not usable for actually using it, but it is certainly usable for reading the code and following along. Okay, so you saw this diagram that Viral used a Photoshop version of this morning in the sponsor talk. This is the architecture diagram for the compiler parts of Cedar. basically, we take in these modeling representation spies, Verilog-A. We compile them into general purpose IR. Then we do some optimizations on them, both structural and ordinary compiler optimizations, and then we code gen them for the numerical solver. But I think it's more interesting than the architecture diagram is how this maps to various Julia packages. So a core aspect of how Cedar is designed is that we reuse core.compiler, the core Julia compiler infrastructure, as much as possible. So all the IR representation, all the general purpose optimizations are just core.compiler. AD is just diffractor. And obviously, we're using SciML for the solvers. We're using the stage selection code that's in MTK. Where exactly that will live is a bit of a TBD, but it's the same code that's in MTK and Julia Sim compiler. So the pieces that are sort of different are the language support for SPICE and Verilog-A, which sits in Cedar Sim, and then some of the code generation at the bottom, which is in DAE compiler. All right. So let's talk about DAE compiler. But first, let's talk about why does DAE compiler exist? We have an amazing ecosystem for solving differential equations. What does DAE compiler do that the rest of the ecosystem does not? And the point I want to start is the raw diffieq.jl SciML base interface for solving DAEs and ODEs. So for those of you not familiar, you basically specify your system as a Julia function, which evaluates the differential algebraic equations, puts the residuals in an output array, and then you can give this to SciML, pass it to the solve function, and all of the hundreds of solvers that SciML has will just automatically work on for your function and will give you appropriate results. And this is a great interface, right? Like it's extremely simple. It's extremely explicit. It'll just run the code many times inside the inner loop of the solver. It'll run exactly what you give it. It'll do AD the standard way to give you Jacobians if the solver is needed. So I'm actually like, I think this is a great abstraction, and it's more powerful than the abstractions that you have in a lot of traditional simulators. So already this is better than the things that traditional SPICE simulators, for example, are built on. But there's some problems with it also. So I think the biggest problem is that we don't have the structural transformations. So all of the optimizations that were in the slide blue on the right-hand side of my architecture diagram, those are not applicable. It just treats the system as a black box. There's lots of explicit indexing in this, so you sort of manually need to keep track of where are my states, where are my derivatives. Partly for that reason, and also for some other reasons, it's not super easy to compose and reuse smaller systems. You might hear me say this representation is non-operatic, which I won't dive into, but there's some mathematical theory on how to compose these systems. There's things like event management and discontinuities, which you need to do manually here. It doesn't track states and parameters other than through indices, and it's also not completely universal over all solver types. So while it's mostly universal, there's still like 3 or 4 different representations that you may have to write manually, and you also have to do, as I said, things like events and discontinuities manually. So it's great, but not perfect. So why not just use MTK? Wasn't MTK supposed to solve exactly this? And partly yes, so it does automatically paper over all of the solver abstractions for you. So it generates all of the different representations of the system for you that the solvers want. It has state and parameter management, and it's a much higher level representation, and it has all of the the optimizations and the code gen and all of the nice things that I wanted. It's built on symbolics, so it's more of like conceptually it's more of a symbolic programming framework, and that comes with a lot of choices and to my mind at least, drawbacks if you're trying to use this as a compilation target for a higher level modeling framework. So there's a lot of global state. Things are indexed, things are identified by the name of the variables. There's lots of global variables. And even if that doesn't bother you, at the very least, the semantics of MTK code are not Julia semantics. They're MTK semantics, and there's some embedding into Julia semantics, but it's something that you have to learn at the very least. MTK doesn't support any explicit control flow, so MTK models are traced out of the Julia representation. They're not compiled. So if you have an if statement or a for loop, those get evaluated eagerly. They don't get delayed into the model. There's some support for pre-compilation by writing out the generated Julia file and Julia code, putting it in a file and pre-compiling that. But it's not as seamless. You have to sort of do it explicitly. And I think most importantly, it's too slow. So Cedar did actually start out as an MTK front end, but we ended up having to do something different to support the size of models that come up in the semiconductor domain. So next question, if it's too slow, why not just use Julia Sim compiler, which is MTK, but implemented better, so it's faster. It's a good choice for making things fast. But from my perspective, it has a custom compiler stack, fully custom LLVM code generator, fully custom IR representation. It still inherits MTK's semantic representations, so the semantic challenges that MTK has still apply to Julia Sim compiler. And now you have two compilers, and I'm already struggling to maintain the Julia one, so I didn't want to maintain another one. There's also some issues around parameter specialization and generating specialized code for different choices of parameter sets, which is a little bit in the weeds, but these semiconductor models are not only large, but they're also parameterized by thousands of parameters. So if you have thousands, tens of thousands of transistors, your models easily have millions of parameters that you may want to manage, which is not a domain that, at least at the moment, works well in MTK. Also, its Julia Sim compiler is newer than DE compiler. So even if I wanted to use it, I couldn't have because it didn't exist. Okay. So now that I've talked extensively about what DAE compiler isn't, let's talk about what it is. So DAE compiler is a way to represent systems of differential algebraic equations as plain Julia code plus a small number of custom intrinsics. So the evaluation semantics are basically standard Julia, but with a non-standard evaluator, sort of similar to the GPU stack. So there are some parts of Julia's dynamism that you can't use, but in general, it's supposed to behave as much as possible like standard Julia code. You can kind of think of it as taking the raw diffq.jl representation and just doing the minimal tweaks to it to enable the structural optimizations and to enable this operatic composability. So a core design goal is to reuse the Julia compiler as much as possible, reuse existing packages in the stack as much as possible. I think right now the compiler is about 4,000 lines of Julia code. I'm sort of hoping that in the medium-term future, a DA compiler with the feature set that it has right now could be maybe written in 1,000 lines of Julia. But we'll have some work to do to get there. It does all of the same optimizations and code generation as MTK and Julia Sim compiler. for DAEs, MTK supports some other system types, but for Cedar, we're mostly interested in DAEs, so that's what it focuses on. It integrates natively with precompiled caching, so it caches the generated code as optimized versions of your model function, just as ordinary Julia caches, native code as optimized versions of your ordinary Julia functions. So that all happens transparently under the hood. It scales to the large models we have in the semiconductor domain, but it is still a modeling domain agnostic tool. So a quick tour of all the intrinsics. So the first intrinsic you have is variable, which just declares a variable. The identity of the variable is the same as the identity of the Julia value that it returns. So while you can give these names, the names are non-semantic. So that's nice for people who already know Julia and know Julia scoping rules, know the rules for how Julia values propagate. They don't have to learn a new system for a second order system for scoping of variables. So it feels very nice to use variables. There's equation bang. So what does equation bang do? Basically, equation bang forces the choices of the variables to be such that the argument to equation bang is 0 or 0 to within solver tolerance at every time step. So it's basically a way to add an equation to the system. And again, the semantics of this are operating through the side effect of the equation bang call, rather than having some other semantics. And the scope / the name of it is again non-semantic. There's also DDT, which exposes total derivatives with respect to time. Under the hood, this uses diffractor, so it has full integration with things like chain rules, so you get all of that automatically. You don't have to manually specify derivative rules for this representation, you just inherit that. There's 5 or 6 other intrinsics for things like partial derivatives, observables, time, discontinuities, but I won't talk about those. If you're interested, you can read the doc strings. So how is this implemented under the hood? As you might imagine, there's a generated function which does some magic. The details of how this is implemented are actually still in flux. This is sort of the whole topic of compiler plugins. And we're still fully working out how those interfaces work. But basically, there's a generated function, and if you give it a Julia function that complies with this modeling representation, uses these intrinsics, it will trade that for a DAE function type, which is the SciML base object that you can pass to solvers to integrate the DAE problem. So semantically, this is reasonably fast at runtime, but it hooks into the compilation stage. So the first time you run this, when ordinary Julia call would do inference and LLVM compilation, this will do the optimization of the DAE system and the code generation for the solver. So yeah, as I said, the exact details of how this works are in flux, but eventually it maps down to a custom abstract interpreter. The details of how that works are extensive and split over multiple talks. So 2 of those already happened, so I'm sorry, you'll have to watch them on YouTube. But basically, what does the custom abstract interpreter do? It provides models for the custom intrinsics that we talked about. So it explains to the Julia compiler how those work. It sets up the caching. It wraps the abstract interpreter that's in diffractor to provide AD support. It has a custom interprocedural analysis. So we added a hook in the Julia compiler, which is used by escape analysis for doing post-inference interprocedural analysis. And this uses the same mechanism. And then it has the custom code generation to generate the various forms that the solvers need. And again, if you're interested in how exactly to do any of these things, there's full talks on basically all aspects of this. A quick look at the custom lattice. So there's a custom lattice element called incidence. What does incidence do? It basically tracks for every value in your function which variables does it depend on. So it explicitly tracks linear combinations with constant coefficients, and then it tracks also which variables it depends on non-linearly. So it might say, okay, this value in your system is A plus B plus some nonlinear combination of C, D, and E. And then it uses that to generate the information that feeds into the structural optimizations. Some other lattice elements also, EC for tracking equation identity, partial scope for symbolically representing the hierarchy of the naming metadata. And then there's partial key value, which is a lattice element to optimize core.generics.key value, which is part of the implementation of scope values. So I think Valentin might talk about that in his scope values talk. Of these, I think all about partial key value are specific to DAE compiler. Partial key value might be moved into base at some point. So what does it do with all of that information? Well, it does these structural transformations. This diagram is not really meant to be understood. It's more for eye candy. But basically, all of the circles are variables, and the red ones are which of these variables does it actually need. So even though the system, and this is the same inverter system that I showed at the beginning, even though it has like 20 variables or so, the structural transformation can see that numerically it actually only needs 3 of them. All of the other ones can be expressed as some expression of those 3 variables. So it reduces the size of the system from 20 variables to 3, which is the same sort of transformation that MTK does. Okay, 2 minutes left to talk about Cedar, 1 minute left. I'll cut maybe into the question time a little bit, so I said the transistor models are large. What do I mean by large? So this is the implementation of one transistor. This is BSIM4, which is a transistor model from the early 2000s. It's about 3,500 lines of code, which is quite a bit larger than even relatively large models for complete systems in other domains. So this is part of the reason why it has a custom compiler stack, is just because of the nature of these models. So all of these 3,500 lines of code define 3 equations in terms of number of equations in the system. So these models are sort of large in number of code. Number of lines of code per statement, but not in number of equations. So there's sort of multiple scaling domains. And if you go to the Julia Sim talk, they're mostly talking about scaling in terms of number of equations. But there, each equation is much simpler. So here, each equation is many thousand lines of code, which is a little bit of a different domain. In general, these models are written in a language called Verilog-A, which has some superficial syntactic similarity to Julia through various kinds of Pascal-derived languages over the years. But it's an extension of Verilog, the language for specifying digital circuits. It has 2 data types, integer and real. It has a C-style preprocessor, unlike Julia. It has language-level intrinsics for AD. A little bit ahead of its time there, since it's from the early 2000s. I think AD didn't really become popular as a concept until deep learning. So a little bit ahead of its time. It has language-level constructs for these equation and variable intrinsics that I mentioned, and was originally designed to be transpiled to C. So how do we implement this? And I know I'm out of time, so I'll go through this quickly. Basically, the core idea here is that we think of Verilog-A as just a very weird way to write Julia, or a string macro. So basically, we have a custom front end, but after lowering, it emits Julia, lower Julia IR, and you get a lot for that. You get LLVM codegen, you get GPU support, you get revise working, you get debugger. Debugger screenshot on the previous slide. You get precompiled, you get caching, and you get all of this in about 6,000 lines of Julia. So for comparison, is that a lot, is that a little? There's a Rust implementation of Verilog-A, very recent, about 70,000 lines of Rust, which I'm not making any claims about like Julia versus Rust, and I'm not making any claims that these have equivalent functionality. I'm just saying like, this sort of semantic domain has complexity on the order of tens of thousands of lines of code, but because we reuse Julia for everything after the front end, we can do it a lot quicker. Similar story for Spice, although Spice is a mess. I won't really talk about it. The one thing I will point out is that we can reuse the Julia package manager for PDK distribution, which is very cool. And the last thing I want to talk about, and this is my last slide, is if all of these languages are such a mess, can we just use Julia for specifying these circuits directly? And the answer is maybe, kind of, would be cool. So this is a way to specify, Cedar has a way to specify circuits directly as Julia code, and in particular, something that you can do is specify parameterized circuits and do parameter exploration, with things like parameterized structs or for loops to generate arrays of things. And I hope to talk about that more next JuliaCon. All right, that's my talk.